Welcome to lesson 39. We're in 39A, radian measure of angles. This is basically going to be a new unit of measure that you can use when you do conversions, specifically for conversions in trigonomic functions. So we're going to have some evaluating problems where we're asked to convert pi in regards to the degree of measure of a sine or a cosine value. So all we need to really remember is that pi is equal to 180 degrees. So let's just do 39.1 and I'll show you how this applies. This problem says to evaluate. Okay, usually that is just a fancy word for solve. And we have 4 times sine of pi over 4 plus the sine of negative pi over 3. So in order to evaluate this, we've got to convert this pi symbol into something that we can calculate. And it's not 3.14. It is going to be 180 degrees. So we say pi over 4 times 180 degrees over pi, because that's what this is here. We had pi in the numerator, we needed it in the denominator so we could cancel it out. Or all you really need to do in this regard is, this is a shortcut, you just need to say 4 sine 180 degrees over 4 plus sine of negative 180 degrees over 3. That's literally all we are doing. Pi, in this instance, it's the same as 180 degrees. So then we would do the math calculation and we would find that 4 times the sine, 180 divided by 4, is going to give us 45 degrees. How easy peasy is that? And the sine of negative 180 divided by 3 is going to give us a negative 60 degrees. So this is the actual problem that we need to evaluate. And we know how to do that. That's that easy. It is that simple. So all we're going to do is first find, this is a positive 45 degrees. So we know it's going to be living in the first quadrant. So we're just going to give ourselves a little reference triangle right here with all the fixins, 45, 45, 90. We know that these two sides are going to be 1 and 1, and that this is going to be the square root of 2. So this is the sine. Sine is so it's opposite over hypotenuse. So 45 degree angle opposite, that's going to be 1 over square root of 2. So 4 times 1 over the square root of 2 plus, now we have the sine of negative 60 degrees. So all we need to do is measure from our initial side instead of our terminal side. That's going to put it in quadrant 4. So we're going to have a 60 degree angle here. So this is 60 and this is 30. This is our 90 degree angle. So that means that we have a hypotenuse of 2 and we have square root of 3 here, and this is a 1. Okay, and this is going to be a negative 3 because it is below the x-axis in that fourth quadrant. That's why it's so important to figure out where these angles live before you start calculating everything. So the sine of negative 60 degree, sine is so that's opposite over hypotenuse, so negative 3 over 2. So because it's negative 3 over 2, this is going to be minus square root of 3 over 2. Now to get rid of this is going to be 4 over the square root of 2. We're going to multiply by the square root of 2 top and bottom. That gives me 4 times the square root of 2 over 2 minus the square root of 3 over 2, which we can normalize or simplify into one fraction. 4 times the square root of 2 minus the square root of 3 all over 2. And that would be the answer that you would put into Jupyter and the way I'd want to see it. So it's that easy. Every time you see this pi, you're just going to substitute in 180 degrees. You're going to convert it. Now you can use your conversion units, but when you just have that one unit and they're equal to each other, there's not another unit of measure here. Sine is not a unit of measure. So just substituting it in is perfectly fine, because what we want is the degree anyway. So let's do 39.2. I'm just going to clear the page, so that'll be faster. All right, 39.2. So here we're going to evaluate the sine of 13 pi over 4 plus 3 times the cosine of negative 5 pi over 3. So again, we're just going to substitute in 180 degrees for pi. So sine of 13 times 180 degrees over 4. 13 times 180 divided by 4, that's going to be the sine of 585 degrees. Plus, this is 3 times the cosine. Now we have negative 5 times 180 over 3. So 3 times the cosine, negative 5 times 180 divided by 3 is going to be negative 300 degrees. Okay. Now we just need to figure out where these live. And we can do that pretty easily. This is a positive, so we're going to subtract 360 from that. 585 minus 360 degrees, that's 5. And this is going to be 2, and this is 225. So this is within our 360 range. So let's look at our coordinate system and figure out where that would be. So this would be 90, 180. So it's going to live here in the third quadrant. So let's subtract 180 to figure out exactly where that is. So 45 degrees. So we have 45 degrees into the third quadrant from the terminal side. So this is going to be a 45 degree angle. This is going to be a 45 degree angle. Everything's going to be negative. Negative 1, negative 1, and then this is the square root of 2. So this is the sine. Sine is so that is opposite over hypotenuse. So negative 1 over square root of 2 plus 3 times something. All right, so we know this is a negative degree. So the negative degree is going to count backwards, right? So if it counts backward 300 degrees, then it's 60 degrees shy of coming full circle. So that means we have a 60 degree positive angle right here, which is good. So this is going to be 30. Here's our right angle. So this one is 1, 2, square root of 3. I believe that's right. Yes, that's correct. So everything's positive on this one because it lives in quadrant 1. So that's what we're going to put in here. And this is the cosine of this. Cosine is ca, so that is adjacent over hypotenuse. So the adjacent is going to be 1 over 2 for the hypotenuse. So that is going to be 1 over 2, just like that. So 3 times that, that's going to be 3.5, or 3 halves, I should say. And we want to normalize this by multiplying by the square root of 2 on the top and the bottom. So a negative square root of 2 over 2. And we want to normalize this, put this in the simplified form. So that would equal 3 minus square root of 2 all over 2. Now that's not what the book has. The book has negative 2 plus 3 all over 2. This is the same thing. And this is the version that Saxon has been telling us all along to use, or the format, and that is with the complex number last in the expression. So we're going to continue to follow those rules and put it in like that. However, if you put it in like this and the system doesn't mark it right, then I will. But go ahead and put it in the rules that we've been following, just because there's some consistency there, and it's more than likely going to be marked right by the system whenever you type it in, because that's the format I'm going to use. All right, so let's look at 39.3. This is not terribly hard. You should feel pretty smart right now, because this is stuff that you already know. You're just adding a little bit of, another little variable to it. It's not a entirely new concept for us. So 39.3 says to evaluate, the cosine of negative 25 pi over 6 minus 2 times the tangent of 4 pi over 3. So when we put in 25, this is going to be cosine negative 25 times 180 degrees over 6 minus 2 times the tangent of 4 times 180 degrees over 3. This calculation becomes the cosine of negative 750 degrees minus 2 times the tangent of 240 degrees. Now we just have to figure out where these live. Now, negative 750, this is going to be measured from the initial side all the way around. So one time around is 360, another time around is 720. So I can take negative 750, because I know that that is more than 2 revolutions of the circle, and I'm going to add 720, which is my 2 revolutions, and then that gives me a negative 30 degrees. So I can measure from the initial side 30 degrees. Here's my right angle, and here's my 60. This is where he lives. So that means that my 30-degree angle, where is he? Oh, I'm on the wrong page. Let me look. All right, my 30-degree angle, I've got the square root of 3 here, and then I've got 1 here, and this is a positive 2 here. So this is a negative 1, positive 3. That is what I'm looking at. All right, so let's do this angle. Actually, I'm going to go ahead and put him in here. This is the cosine. Cosine is ca, so that's adjacent over hypotenuse. So the adjacent side is square root of 3 over 2. So square root of 3 over 2 minus 2 times whatever the tan of 240 is. All right, so we're going to find the tan, which is TOA, and I'm pretty sure it's going to live in the 3rd quadrant, because the full 3rd quadrant would be 270 degrees. So 240 minus 180, which would be from here to here to here. Sorry, 90, 180. That's going to be 60 degrees. Yeah, that's going to be a positive 60 degrees. So 90, 180, 240 is going to be 60 degrees right there. And this would be my 30. So this is going to be a hypotenuse of 2. This is going to be a negative square root of 3. And this is going to be a negative 1. So those are all, these two are negatives. So TOA is opposite over adjacent. So these are both negative. So a negative over negative is a positive. So the opposite is negative 3 over a negative 1. So if you have a negative square root of 3 over a negative 1, guess what? That just becomes a positive square root of 3. And we can just remove the parentheses and put that together. So now we have 2 times the square root of 3, and we want to add these two together, so we need to get a common denominator. So we're going to multiply this times 2 over 2. So we end up with the square root of 3 minus 4 times the square root of 3 over 2. There's an invisible 1 here. They both have the same radical base, so we can actually subtract. So our answer is going to be a negative 3 times the square root of 3 all over 2. Easy peasy. That was not so hard. All right, let's do 39.4. We're going to apply this a little bit differently. So let's look at this. Let me clear the page. 39.4, and let me put this up here for us. I'm going to have to draw an illustration for you. All right, 39.4. The latitude of a point on Earth is the degree measure of the shortest arc from that point to the equator. So that's this right here. The latitude of Los Angeles, LA, here, is 34.05 degrees north of the equator. So if we come from the center of the Earth straight out to the equator, and then we measure that central angle up to LA, we get 34.05 degrees from the center of the Earth to LA, and then from the center of the Earth to the equator. How far is it from LA to the equator if the diameter of the Earth is 7,920 miles? So remember, our unit of conversion is pi radians is equal to 180 degrees. So here we're given degrees that we need to convert into radians, which helps us find the miles. So let's look first at converting this into radians. So 34.05 degrees times pi radians over 180. So the degrees would cancel each other out, right? So we would get 0.594 radians. So that's what we had to do, was convert 34.05 into radians. So when we divide 34.05 by 180, we get the radians of 0.594. Let me show you how to do that on the calculator. So 34.05 divided by 180 equals 0.189166666 times 3.14. That's 0.5939, which rounds to 4. Right. So that's where we got 0.594 radians. We substituted in the value of 3.14 for the pi value here to get this radian value. Therefore, if the measure of the central angle were 1 radian, the distance from Los Angeles to the equator would be 1 radian times 3,960 miles. Why? Because 7,920 is the diameter. So a radian would be half of that because, you know, that's a radius, radian, right? That would be 3,960 if we divide that by 2. So we take the radian and multiply it by the value here to get the distance. So this would equal, the distance would equal 0.594 times the radian, which is 3,960 miles, which would equal a distance of 2,352.24 miles, because this unit of measure is mile right there. And that would be what we would do. So your radian value is going to be the length of the radius. Every time you have a radian here, you're going to sub in the length of the radius of that sphere. That's what we're doing. Does that make sense? And for pi, you sub in 3.14. And that will get you an actual number. If you don't sub in pi, then what happens is this. Let me show you on the calculator what that would end up being. So you would have 34.05 divided by 180. So you would have 0.19, sorry, I didn't write that right. That would be 0.189, let me look at my calculator again, 2 pi. That would be what you'd have radians. So you would have 0.1892 pi times 3960. Well, we're past the point of leaving pi when we are having a very difficult or lengthy calculation. You now have permission to sub in 3.14 to do that, to get an actual distance, right? If you had not done the pi, you would have ended up with 0.1892 times 3960 pi miles. That would be the formula that you're using, because this is your radian length. Does that make sense? This would be that. And these are all three factors. All right. I guess the more accurate way to do that on the calculator would be to say 34.05 divided by 180 equals times 3960 for the radian length. And then that would be times pi on the calculator would equal, see, that's actually a different number. So if you do pi on the calculator, it's going, that's why I don't like to use the calculation of pi, because it gives you a different number when you do it on the calculator versus when you do 3.14. All right. Okay, so this is where the decisions are made. How do I want to address the accuracy? I think what I'm going to do is I'm going to put both in the system and let you choose. And then that way you'll be able to do either one. I want you to do either one. Because when you get to college, it's going to be the choice of your professor. He's going to tell you what he wants you to use, whether he wants you to use 3.14 or whether or not he wants you to use the pi on the calculator. So now I will say, as always, this one is the less accurate. This is just the rounded off red-headed stepchild of pi. This is still the most accurate one. If you were to do 0.1892 times 3960 and have 749.232 pi. So 749.32, what did I say that was? 232, sorry. 232 pi miles. That's the most accurate of all of it. That is the most accurate of all of those versions. So I think what I'll do is I will put this in, and I will put this in, and then I will put the calculator version in, which is 2353 point whatever that was. And that way, whichever way you do it, you will get it marked right. this is going to be the most precise. But when you get to college, your professor is not going to want to see that unless they care about precision. If they just care about you, it depends on what field you're going into. If you're going into science, then this may be the one that your professor wants to see in that class. If you're going into mathematics, then 3.14. If you're going into mathematics education, then 3.14 is the one that they're probably going to want you to use. If you're going into mathematics for precision, then they'll want you to use the one on the calculator. So it depends on your discipline as to whether or not you use that, or as to how your professor wants you to use that. So just be aware that there are 3 possible responses to this. And I want you to be able to do all 3 of them and understand how to get all 3 of them and know how to ask that question when you get to college so that you can have the best score possible. You know, you want to be able to give the professor what they want in the way that they want it. So recognize that you are going to get 3 different answers, or at the very least 2 different answers if you use pi 3.14 versus the calculator pi. Okay. All right. Moving on, we have one more problem in 39A, and then we're going to move on to 39B. So let's clear the page. I hope that problem gave you an applicational use of radians where you can actually see where that might be handy in the future. So let me pause and write this up here because it's kind of long. All right, so in 39.5, Theo measured the angle between the base of the building and the top of the building and received a reading of 0.6 degrees. If Theo is 4,000 feet from the base of the building, how high is the building? Okay, so we can agree that 0.6 degrees is a very small degree. So I'm going to show you something right quick. I'm going to zoom in to this building if I can. Let me come in here and zoom. So what we have here, we're going to look at radians, but what we have here, we're going to have an arc, right, from here to here. A little bitty arc, because this is a circle, right? We're measuring in radians. For very, very small degrees of measure, the chord is almost the same length as the arc. They come really close together. I'm not doing a very good job of illustrating that. This is the chord, and this is going to be the arc of the circle. Those are almost the same length. They're very, very close together. The chord is the straight up and down part that connects the 2 points of the angle, like in a triangle. The chord is, or not the chord, but the arc is the part of the circle that is the degree, right? That is going to be the same as the 0.6 arc. And because they're so close together, we say that the chord is the same length. So let me bring this back down to where we can actually see what we're doing and have some room to work the problem. Let me switch back over here to this color. All right, so because of that, when you zoom out, you see they're almost on top of each other. But there is a little degree of separation, but it's so close that we just accept, let me make this a little bit bigger, we just accept that they're the same. We give it the benefit of the doubt. So then we just set up our problem with this degree of measure at this radian, right? So we would say 0.6 degrees times pi radians over 180 degrees. So the degrees would cancel each other out, and we would say 0.6 divided by 180. Let's do all the different permutations. So we would have 0.6 divided by 180. So that would equal 0.00333333 pi radians. Okay, so let's write that down first. That would be 0. Is that 0? 0, 0, okay. 0, 0, 3, 3 with the 3 repeating pi radians. Okay. The radians we know is going to be the radius of the circle. This is the radius, this is the 4,000 feet. So we can sub in 4,000 for the radians. So we can go ahead and we can multiply that number by 4,000. So times 4,000. There's going to be 13.3 repeating times pi. Right, so then that would be 13.33, and we'll repeat the 3 times pi. So now we can either do, and this is feet, because the unit of measure here was feet. Now we can either do pi as 3.14 feet, or we can do pi on the calculator. When you have a repeating decimal, it's a heck of a lot easier to do the pi on the calculator. So let's just do that. Times pi equals, and that's 41.8879, which we could round this all up to 41.89. And surprisingly, that is exactly what the book has, 41.89 feet as the height of the building. So you see how that kind of breaks down. You have to take the degree of measure times this whole unit of measure, pi radians is equal to 180 degrees, right? If we're doing degrees, we flip it so degrees is on the bottom so we can cancel the degrees and get an actual unit of measure measurement. Because the unit of measure is going to fall in the radian. And pi is just your typical circumference value that gives you the length. It extrapolates it in relationship to the arc of a circle because it's hard to measure the arc of a circle. So that's what the pi is there for. All right, that is all I have for 39A. I want you to do the practice problems for this section and then move on to 39B.